Think of that. So I don't think of $1 billion, of course. Think of innovation. Think of innovation. Just tell your kids to be innovative when you have kids. Long way ago. But, or think yourself right now. You have time. You guys are what, 25? 21, 22? How cool. That's amazing. Young kids, you are young. You have great energy for next 15, 20 years. I am old. My energy is dying. But as I said, the most prime time of your life, if you have not realized it, is 20 to 30. Prime time of your life. Remember, nature made us to breed. We're young, 20 to 30 years old, young people, right? After 30, 40, you become old people. Nature does not want you anymore. Creates lots of cytidine deamination, which is reality. You know what happens with deamination? Deamination increases with aging. So all the deamination creates mutagens. That's how you get cancer. C2T mutations are most prevalent in cancers. C2T mutations happen by deamination of cytosine, 5-methylcytosine. Remember 5-methylcytosine deamination? Cool, right? I have a lot more deamination than you do. So enjoy that till it lasts. Use it. Use it to be innovative and creative. Okay. Did I have more slides? What's the time? 4:11. Okay. Oh. I'm burning more calories by speaking than running and walking these days. Got this? We were here. DNA is another technology is called MNase-seq. MNase is an enzyme that will cut until it finds a nucleosome or any binding factor. Okay? So it cuts and degrades the DNA till it finds it. So what happens is it's going to bind here and it's going to kill it. And then you degrade the protein by proteinase K treatment, remember? And then you just got whatever DNA remains is going to give you a peak. It's completely inverse of DNase or ATAC-seq. Okay, cool. So you see the profile in the bottom? MNase-seq tracks with where nucleosome is. DNase-1 or ATAC-seq tracks where there is no nucleosome. Complementary methods. Okay, nobody does MNase-seq these days. But it's a very important method if you want to understand where your protein of interest is. MNase was tagged with the antibody in the cut and tag. So rather than ChIP-seq, when they do cut and tag or cut and run, I'm sorry, they just treat, they just cut it with MNase. They just fuse the secondary antibody with MNase. So your antibody binds here. Let's say to your histone modification of interest, your secondary antibody binds there, has an active MNase, cuts out the right here behind. Oh, come on, cuts out right here. Okay, so now MNase is used innovatively to cut this portion in a ChIP-seq, so rather than doing now ChIP-seeking, etc. Now he's just cut it and he has the DNA ready to go. That's why it's much faster protocol than ChIP-seq is, and companies now sell it. Lots of people buy those kits. Again, business ideas. Simple things. He knew MNase, he knew ChIP-seq. All he did was created a conjugated version of secondary antibody with an MNase. That's all. That's IP, intellectual property. Simple. Got it? So you can create a lot of stuff. Lots of methods as well if you want. This is just how you do the computational analysis. I'm sure you guys are not going to do this, but I just wanted to remind you how it is done. After sequencing, you get FASTQ files. FASTQ files you align to the genome. You get BAM files. Once you align, BAM files, after that you clean up stuff, and then you go in, you do peak calling. In this case, you do nucleosome calling. In DNase or ATAC, you do peak calling, and then you do your analysis and max peaks, right? And then you got whatever you wanted. You do transcription factor motif analysis, and you know what transcription factor is binding with. Okay, cool. ATAC-seq. You going to cover this again? You guys got this or no? How many of you did not get ATAC-seq? Can I need to repeat it? Okay, a lot of you did not. Here's our chromatin, left side. You remember this? Closed chromatin, open chromatin. There's a TN5 transposase. It has a blue and a red adapter to it, like it puts on wherever the open chromatin is. You see where it goes? TN5 transposase along with the adapters, right? And you essentially clean up the rest of it. So what you're going to be left with is your adapters with your black sequence, which is open chromatin. And that's it. You clean up the rest. That's it. Done. You got your enrichment of nucleosome free region. Okay? Cool? So enables measurement of this, whatever. Does not require antibodies or tags. It's simple. It's a hyperactive TN5 transposase used to fragment the DNA and integrate into the active uses. What I forgot to tell you is that TN5 transposase itself can just break the DNA, because in this case you don't need sonication or anything like that. It just breaks the DNA also, because it naturally knows how to transpose its DNA in there, right? So it knows how to cut it, transpose its DNA. Instead of that transposing its own DNA, now it's transposing the ligand adapters. And now adapters are ready for you to PCR and make your library. Now do you get it? Still, how many of you don't get it? No? Okay. Yeah, so this works very well. It works in small number of cells, etc., etc. So you can get it. Okay, so two-step protocol. Insertion of TN5 transposase with adapters. I think I've repeated like 50 times by now. And PCR amplification next to it, I'm using the adapters. Okay. The number of cells you need, says on the left, is very small, whereas for DNA-seq, etc., you need large number of cells. This is much easier. So now a lot of times you don't have enough number of cells because you're dealing with tumor, you're dealing with stem cells, you're dealing with different cells which are not there a lot in your body. So there it works. So methods that work in small number of cells actually get adapted for various purposes. Makes sense, right? Here is what I was telling you earlier. There is you see the size, fragment length. Fragment length means where the adapter was put on. And you can see this is less than like 50 base pair here. Then you have another one that is around 170 base pair. Then another one around 340 base pair. Another around 510 base pair. So that's single nucleosome, two nucleosome, three nucleosome, and all that. Makes sense, right? Because your structure, chromatin structure is like that. One nucleosome, two, and three. So it hops on here. It's going to amplify that. Cool? On the y-axis is normalized read density, because the larger and larger it becomes more and more difficult for PCR to amplify. So there will be less and less number of those reads you will get. The shorter fragments amplify faster, right? By your Taq polymerase, or you don't know this, but you should know this. Okay? If you run PCR practically, and this knowledge doesn't come unless you have really practically done PCRs, you don't appreciate it, but PCRs work really well in when you're amplifying small amount of DNA. If you're amplifying larger amount of DNA, it works, but the efficiency is much lower. So that's why you see this thing go down and down and down, because as you go to larger hexamer is larger number of number of base pairs, right, that you're amplifying, and that does not work. Cool? You got that? Did I teach you something? Did you know this? You didn't know this? Okay. All right, we'll not worry about the bottom one. Anyone else? Questions on ATAC-seq? ATAC-seq is done. This is the last slide. Questions? No? So ATAC-seq, again, you do the same thing, QC of your reads, you do your alignment, you do your peak calling, you do your QCLS, and then you do your downstream analysis. Downstream analysis means you do motif enrichment, pathway analysis, to know which transcription factor sites are there, which pathways are enriched, etc., etc. Okay? Cool? We good? Done? You want to go home, or I should teach you a little bit more? That slide deck is done, huh? Done for today? You guys want to do methylation today or tomorrow? Tomorrow? You guys are like, okay, I'm done. Please let me go, let me go, let me go. Right? How many of you want to be let me go? How many of you want me to keep talking? Because you love my voice. What? You want to keep listening more? You're like, okay, all right. Well, go, please do it. I can actually talk about it tomorrow. I think it's probably enough for today. Trying to figure out where were we. Actually, let's talk tomorrow. Okay? Only because I think you guys are saturated in your brain. Somebody sitting through 6 hours of lecture for 5 days continuously. I can understand how your brain is right now. 4 or 5 hours. Where is DNA methylation? When did I teach you guys DNA methylation? Yesterday? Huh? Was it lecture 2, right? PDFs. Yeah. 420. Yeah, this is it. This was what I was doing. Yes, we haven't talked about these. Let's do it tomorrow, guys. I'm tired. What? You guys want to hear more? You're like, you're like very happy. Okay, all right, I get to go. And then you're also like, okay, sir, please go ahead, sir. No? Bisulfite sequencing. Should we get started? 45 out of 64. So there are like 20 plus slides here. We'll do it tomorrow. Okay? Any doubt?